I have a set of all the numbers which are co-prime to 9. So 1, 2, 3 is not co-prime to 9. 4, 5, 6 is not co-prime to 9 because 3 and 6 they share a factor, that is 3 with 9. And then 7, 8. We are only considering positive integers which are co-prime to 9. And the operation is multiplication modulo 9. What does it mean? So we'll see that directly with the multiplication table or Cayley's table. One will have the same row. All the elements will remain the same when multiplied by 1. 1 is the identity, of course. When you multiply by 2, now 2 into 2 is 4, 2 into 4 is 8, 2 into 5 is 10, but 10 mod 9 is 1. 2 into 7 is 14, but 14 mod 9 is 5. 2 into 8 is 16, but 16 mod 9 is 7. 4 into 2, now okay, it will be symmetric. So what we'll do is let's just fill the diagonal first. Okay, this is the diagonal. Next entry that we'll try to fill is 4 comma 4. So 16, 4 into 4 is 16, 16 mod 9 is 7, 5 into 5 is 25, 25 mod 9 is also 7. Okay, and 7 into 7 is 49, 49 mod 9 is 4, and 8 into 8 is 64, 64 mod 9 is 1. So we have filled the diagonal, and now we'll fill only the entries above the diagonal, that is 4 into 5 is 20, 20 mod 9 is 2, 4 into 7 28, 28 mod 9 is 1, 4 into 8 is 32, 32 mod 9 is 5, then 5 into 7 is 35, 35 mod 9 is 8, 5 into 8 is 40, 40 mod 9 will be 4, and 7 into 8 is 56, 56 mod 9 will be 56 mod 9 will be 2. Okay, and then we fill it symmetrically. This will be 2, and symmetrically this will be 4, this will be 8, this will be 5, 1, 2, and this will be 7, 5, 1, 8. It is symmetric because it's multiplication of two simple numbers, which is a commutative operation. And from this we can say that yes, it is closed, because all the numbers over here are also the numbers from our set A, which is numbers co-prime to 9, positive integers co-prime to 9. Okay, so closure is done. Next is associativity. For associativity, we know that multiplication is associative. Multiplication of numbers is associative. So I'm skipping that step right now and I'm moving ahead. But in exam, you will have to show with at least one example. Just take any triplet, any three numbers, and prove the associativity. Then we go for identity. Identity, as we saw when filling the table, 1 is the identity. Again, you will have to do it in detail. Now inverse is interesting. For inverse, we'll have to find the inverse of each, right? So we'll say that x and x inverse. We'll try to make a table sort of a thing. Okay, so now for 1, where is the identity in each row? So here we have identity. So for 1, the inverse is 1. For 2, there is 1 over here. So for 2, the inverse is 5. For 4, the inverse is 7 because 1 is in the column of 7. Then for 5, because just like you can simply say that 2 is the inverse of 5, 5 is the inverse of 2, vice versa is also true, always true. 7 is the inverse of 4, 4 is the inverse of 7, that will also be true. Now for 8, 8 is again the inverse of itself, right? So this is the inverse. Now inverse exists for all the elements, therefore it's a group. Okay, and moreover the operation is commutative, therefore it's an abelian group. So it's a group, and it is also an abelian group. Okay,